So today I'd like to talk to you about quantum dots now that we've laid the foundation for the understanding of the quantum dot with our discussion of the infinite square well in quantum mechanics and a review of what wave functions are. So what are quantum dots? Well, quantum dots are semiconducting nanocrystals, and their electronic properties are governed by their size and shape. Generally, they're less than 10 nanometers in diameter. And they were first developed in the 1980s at Bell Labs. Now, the term quantum dot was actually coined by Mark Reed, a physicist from Yale, who was also working on quantum dots in the 1980s. The dots are named that because of their quantum confinement properties of the nanocrystals that lead to their interesting fluorescent colors that you see in this image here. Now, as the size of the semiconducting material shrinks, the band gap widens, and that's because the electronic structure goes from those wide, near continuous bands that you get in a bulk solid to the narrower bands with fewer discrete states, closer to what you might see in a molecule, right, where you have just a few jumps. Now, by carefully controlling the size of the dot, you can precisely determine the color of the fluorescence that comes out. And this makes them really useful for a wide range of applications. So in this image here that I borrowed from Sigma Aldrich, you can see that you have this sort of near continuous band structure in a crystalline solid. And then as you drop down the size, there's fewer and fewer available states. And what that does is it makes the gap between those states wider as the particle shrinks because the states get fewer and fewer and fewer. Now, there's a formula for the band gap that's pretty easy to understand if you remember your introductory quantum mechanics. The energy of the band gap of the quantum dot differs from that of the bulk by the following formula. The band gap for the nano-sized particle, E gap nano labeled here, is equal to the energy gap for the bulk plus this additive constant. Now that constant is h squared over 8r squared, where h is Planck's constant and r is the radius of the particle, and then times 1 over the effective mass of the electron plus 1 over the effective mass of the hole for the exciton or electron-hole pair that's generated when an electron in the quantum dot absorbs a photon of energy. So in that circumstance, the electron is excited out of the valence band and into the conduction band, leaving behind a little hole in the valence band. So that's hence electron-hole pair, or exciton if you're referring to them as a pair. Now the effective masses for the electron-hole pairs are usually fractions of the electron mass. So for example, in some of these nanocrystals here, 0.13 times the electron mass and 0.45 times the electron mass for the electron and hole masses respectively are approximations. And there's corrections to the equation that you'll hear about in later lectures that I'm going to post under this one if you'd like to reference them. Now, that expression for the offset to the band gap energy for a nanocrystal as opposed to the bulk should look familiar. So remember, when we talked about it in modern physics or introductory quantum mechanics, we covered the energies for an infinite square well potential. And those energies were h squared n squared over 8mL squared. So that second term that we just talked about is basically exactly the same structure as that for an infinite square well potential. And this is such a nice relationship that quantum dots have actually been suggested as visual aids for helping teach students about particles and infinite square well potentials because it maps so nicely. If you just take the length of the box and instead of the length of the box you put your radius of your nanoparticle, and instead of the regular mass of the particle confined to the well you put in the effective sum of the masses of the reciprocals of the electron and hole pairs, boom, there it is. There's the formula. So, fluorescence of quantum dots is a property that's exploited in a lot of different applications of quantum dots, and so I'd like to explain a little bit of background on what this is. Fluorescence is defined as the absorption of a higher energy or shorter wavelength light, followed by the emission of a lower energy or longer wavelength light. And this happens a lot in quantum dots. What happens is you excite an electron from the valence band into the conduction band with a high energy photon, say blue light or ultraviolet light even. And then it's excited into one of these higher level states, and then through a series of steps, it decays down back to a less excited state. But it does it in several steps, and so instead of one high energy photon, you might get multiple lower energy photons, or it can even de-excite through non-radiative pathways and then radiate a photon when it jumps across that band gap. Okay. Now, for that reason, the fluorescence for these quantum dots is going to usually correspond to right around the band gap energy, which is a small spread in the emission spectrum from these quantum dots. So they have really nice narrow emission spectra as opposed to a lot of other fluorescent type materials which have a broader band. So that makes them really useful for a wide range of applications. Quantum dots are actually relatively easy to make in certain ways and certain techniques. Of course, you can use more complicated techniques that we'll talk about, like molecular beam epitaxy, things like that, that might be more expensive, more work intensive. But you can also manufacture colloidal quantum dots using pretty simple and relatively inexpensive wet chemistry techniques. For example, this MIT grad student here from Dr. Bawindi's research group is showing off his setup where they're making quantum dots in the lab using some wet chemistry techniques. Now, the tunability of the band gap combined with the ease of fabrication of many of these quantum dots makes them ideal for a wide range of applications, especially ones where color is really important, like displays. There's even a new type of display, the QD LCD, that was rolled out in 2017. I've posted a link to that, a really nice video explaining this new technology here. Be sure to watch it. But just briefly, what's happening is they're combining LCD displays, which have become so popular and are so prevalent in the market, with some new quantum dot technologies to make the colors, especially the colors in the red, pop out and have a more vibrant and wider color spectrum available in these displays. And very briefly, this is because the quantum dots can absorb that higher energy light that's used to illuminate the back of a lot of these LCD displays, like blue. And right now the LCD displays are kind of heavily weighted towards the blue end of the spectrum, and they're not so good at fluorescing or showing you colors in the red end of the spectrum. But with the new quantum dot displays, they can absorb that incoming blue light and then radiate very specifically in the red, which makes those red colors pop, which was traditionally a problem with LCD displays. There's a video here that explains that a little bit better than I just did, so please watch that for more information. Now, the tunability of the band gap also makes them ideal for applications where you need a wide range of light absorbed. And if you don't immediately think solar cells here, then you're not thinking like a lot of the researchers that are on the market that are trying to bring products to market now. So a lot of work is being done in this area in trying to exploit quantum dots and use them in solar cells, especially for thin film application solar cells where you might need a lighter weight type product. And that's because the energy that comes from the sun is over a wide range of wavelengths, and so it's difficult to craft something that will absorb the light over that broad range of wavelengths, making the efficiency of solar cells maybe a little bit lower than what they might have been. So if you incorporate these quantum dots, you can put quantum dots of a wide range of sizes, which means that they would absorb over a large range of the spectrum that comes from the sun, making the solar cells more efficient. So for more information on that, please be sure to watch this YouTube video that I posted. Also, the tunability of the band gap makes them ideal for applications where you need specific frequencies of light absorbed, like photodetectors. So there's been a lot of excitement lately about using quantum dots in infrared imaging for night vision goggles and things like that. Okay, so I put a link here for an article on this that you might want to read. And finally, one of the areas of excitement has been to use quantum dots and other nanoparticles, of course, for cancer research. So to understand how that might happen, let me first explain about fluorophores. So fluorophores are fluorescent chemical compounds. You might be really familiar with green fluorescent protein because its discoverers won the Nobel Prize in 2008. So fluorophores are used as dyes for staining targeted structures to gain contrast in biological imaging. For example, here is a human cell that's been stained with some different colors to fluoresce so that you can see specific structures within the cell. Now, quantum dots aren't technically fluorophores, but because they are fluorescent materials, there's been a lot of interest in using them instead of traditional fluorophores. And this is because the quantum dots have some advantages. They're very bright compared to the traditional fluorophores, and they can fluoresce in a wide range of colors, and they're also very stable. In particular, there's a lot of research groups that are currently investigating quantum dots as biomarkers for cancer research. See, you can tag the quantum dots with ligands or compounds on the outside of the quantum dot, and then those ligands preferentially bind to cancer cells in some cases, and that could make them very useful for both the diagnosis of cancer and also its treatment, as is shown here in this cool little image where they're marking a tumor with some fluorescent quantum dots that fluoresce in the red. So hopefully that's given you some ideas about how quantum dots work and what they could potentially be used for. And as always, I'm here if you have any questions, and I'll see you next time.